Okay, so first of all, let me thank Camilo and Tom for the opportunity to spend the year at the Institute. It's really marvelous. I think it took me a little while to get settled, but I'm just in heaven right now. So this is work that began with my student Vivian Healy's thesis. So she's currently a postdoc with Greg Lawler at Chicago. It was kind of an exploration because I wasn't sort of from this area, but it was a there was a set of problems over here that now I find very appealing. So, in some sense, I didn't know what to expect of the audience, so I thought I would start with the very beginning. So the very beginning of my work is I've always loved the sort of dynamical systems proof, let me say, of the Riemann mapping theorem, which is the first complete proof of the Riemann mapping theorem. So the Riemann mapping theorem, as we all know, says that every simply connected region in the plane, other than the plane, is conformally equivalent to the open unit disk. And so Kobe's proof is this proof where you construct, it's an actual construction of the conformal map by iterating the square root mapping. So these images on the right, so most of my talk will be on the blackboard. I just want to show you some nice pictures before I get started to sort of set up what the three basic elements of my talk are. And so what's going on in Kobe's proof is that you keep using the square root mapping. So you start with a domain which is within the disk, and then you keep expanding it using the square root mapping. And so if you apply it to some sort of snake or some sort of S-type domain, those are the kind of images you get. But the real reason I care about Kobe's proof is that somehow about 20 years later, in the early 1920s, Loevner came up with sort of a continuous time version of Kobe's proof. So Loevner's proof is a constructive approach to the Riemann mapping theorem. And so it's usually first stated just for slit mappings. Okay, so what's going on over here is that my domain is a slit domain in the complex plane. So there's a parametrized curve gamma of t. And we try to find a conformal mapping that takes this curve into the upper half plane. And what you do is you get the conformal mapping that wipes out, in some sense, the entire curve by basically sort of unfolding it in continuous time. So there's a sort of flattening. So this map GT basically takes the point gamma t down to a point ut. And Loevner wrote down a differential equation to sort of construct the conformal mapping as a function of this point down here. Okay. So the Loevner differential equation is going to be sort of the key aspect of my talk. And I'm going to state it in a slightly different form. So an essential aspect of the differential equation is basically that you have a family of measures continuous with left limit. So this is the kind of standard probability theory convention. So right continuous in the weak topology. And let me define anti-Herglotz function. C minus S, mu TTS. And I'll sort of state a differential equation. So differential equation is going to be the following. And there's going to be sort of an equivalent formulation, which is going to be the transport equation. Partial ZF. Okay, and so over here Z belongs to H, which is upper half plane. And the initial conditions for both of these guys, so f of Z0 is equal to Z, G of 0Z is equal to Z. So these are sort of the core differential equations, but what's going on with these differential equations is basically the following. So somehow over here, I'm going to have some sort of domain in the complex plane. And this set over here, so these guys, so let me call it the boundary. informally, this is the kind of boundary that I'm drawing over here. So this is a set of hulls. And what's going to happen is that my mapping GT is going to go this way and give me the upper half plane. And the mapping F is simply G inverse. Okay? So it's this beautiful differential equation. So the theorem is that if the mu-t's are right continuous with left limits, you solve this differential equation, and you will find a set of mappings that basically take you from a set of regions over here which are slowly being wiped out, just like in the case of the curve. And conversely, somehow, if I have a set of regions that's being wiped out, then I can, and it's monotone, then I can actually write down this differential equation. So what I want to do, and what's going to go on in my talk, is somehow to use this differential equation as a constructive tool to actually construct interesting conformal mapping. So at some level, I'm doing a very basic problem in, a very classical problem, which is how do I find interesting conformal mappings? And the kind of what I mean by interesting is really coming from statistical physics, in particular, two sort of famous models in statistical physics. So one of them is this one. So this is sort of two images which I stole from some paper on the web. So this is a genuine physical experiment on fluids of a Healy-Shaw cell. But this guy on the right is a cluster which is created by a very elementary algorithm. So you start out with some seed. So it's sort of a model for the growth of a cluster. It was introduced, it's called diffusion limited aggregation. It was introduced by Witten and Sander in a sort of classic paper in the physics literature in 1981. And the model is just the following. So you start with a seed, and then you imagine sort of releasing a particle. So it's all, you're sitting in 2D lattice. You've got a seed. You release a particle at infinity. It sort of keeps diffusing along the lattice until it touches the point. It sticks at that point. Then you release another one, and you keep going. Okay, so what happens is that you have a sort of a model for the growth of a cluster by random aggregation. And it's called diffusion limited aggregation because it's sort of you've got a seed particle which is diffusing around and joining the cluster. Okay, so I'm not specifically going to work on DLA. It's a famously hard problem. There are very few results on DLA, but I'm definitely inspired by DLA. So one of the things that you see in external DLA is these crazy tree-like shapes. And the goal basically for us is to find a constructive way of building conformal mappings which are trees. Okay, so a little while after DLA, there was a kind of modification of DLA which connects back with conformal maps. And so this is called the Hastings-Levitt model. And the Hastings-Levitt model is basically, it's a bit like Kobe's proof. What you do is you start out with some elementary conformal mapping. So over here, the elementary conformal mapping is something that takes a disk and it adds a spike to the disk. And then you just keep repeating this again and again. So for various reasons, it was kind of easy to do computations with this. So this is, again, sort of pictures from their paper going back to sort of 1998. There's a parameter in the model which relates to how exactly you add the spike. Again, that's not particularly important. But what's kind of clear is that there are these models out there in the physics literature which basically are sort of creations of interesting conformal mappings.
No, I don't understand how this mapping is defined here. Can you tell us a little bit about that?
If you really want to see it, I'll have to go out to a slide that I skipped.
I'm a little too fast for me here.
Yeah, let me just, well, it's not, it's in some sense, it's, oh, great, it's not even that one. Okay. Let me just show you. So you pick, so this is like you pick a basic conformal mapping. Yeah. So this is like an exact formula for the mapping on the exterior domain, which adds a spike. Okay, so it's something which you look up and yeah.
That mapping adds a spike?
That mapping adds a spike.
Okay.
So it's not particularly, so no. But anyway, and this mapping has got sort of a parameter in it, which is kind of like the length scale of the spike.
Okay.
And then what you do is you sort of keep iterating. So maybe I should have shown you this. So you sort of, the location, so it's a mapping which is defined on the disk. So you sort of, there's an angle parameter on where you add the spike. So that's the theta. So there's your basic mapping, which is given by some formula. There's a theta which you choose to be IID uniform on the circle.
Yes. And
then you just keep iterating a conformal map. So you just build a conformal map by iteration, which is this idea going back to. But over here, you've just chosen.
Theta's not, there's no randomness here?
So theta is random. So theta is IID. So you have a sequence of IID thetas. You could make the lambdas IID2 or something like that, or you could just fix it to be a particular number. So there are various. There's another parameter which sort of prescribes the probability at which it attaches. It's this like there's just like zillions of numerical computations of
So
this kind.
What is actually known about this?
Essentially nothing. So that's the point.
Okay.
So okay, that's not fair. So there are results on DLA. And these results on DLA are you start with the lattice model and you prove theorems that basically say the lattice scales at a particular size. So in DLA, there are two models. There's internal DN and external DLA. What I showed you is external DLA, which is growth of a cluster. There's an internal DLA where you start with a seed and you count, you sort of see the motion from the seed to the boundary. So in that one, there are results by David Jarrison, Charlie Smart. I think it goes back to Maury Bramson and people like that. But internal DLA is not what the physicists call DLA. And on external DLA, there are basically three papers, one of which is a bound of Kasten, and there are two papers which are improvements of Kasten. So in some sense, despite the sort of amazing stuff we know about SLE, we know essentially nothing about DLA.
Yeah. No, so the other question I had is what you've written here with this equation. To what extent is that? I don't understand how that's quite related to.
Yeah, so it's going to be, so it's related in the following sense. So what the punchline of this talk is basically the following. So A, we have a model which gives us a way of constructing trees, embedded trees in the upper half plane.
So this is a substitute for Loebner, or?
No, so our point of view is that we don't start with lattice models, we just do everything consistently with Loebner. So I'm going to sort of have a particle model.
This is Loebner over here?
So this is Loebner in general. So Loebner is just a general way of constructing conformal mappings. And the input to Loebner is a driving measure. In the case of slit mappings, the driving measure is an atom at a particular point.
Okay.
SLE, sort of the most famous of the slit mappings, is where you have an atom, but this atom sort of moves around with the Brownian motion, and the scale in front is kind of critical for the properties of the process. And our goal is actually to do stuff over here when this is a genuine measure, not just an atom. So it's got somehow it's spreading around. There are many different parts that are growing. So that's why I kind of drew this picture. So my goal is to construct pictures of this sort using Loebner theory. Okay, so, okay. Let me just see this. So in some sense, the pictures were really just to tell you, like, there's this physics stuff out there for which we know nothing. And what I want to do is to use a set of probabilistic tools, which are not traditionally used in this area. And I want to sort of tell you about these tools because they kind of play a critical role in our choice. So somehow what I want to do is to build trees, just because in DLA I see a tree, in HastingsLevitt I see a tree, and I would like to find at least one example of an actual tree, like a sort of model of a conformal process, which is using trees where I can actually say something interesting. Okay, so why do I believe one can say something interesting? Well, there's a sort of a set of results that go back about, I guess, now 30 years in the probability theory literature, which basically deal with limits of trees. Okay, so a tree is a combinatorial object. So I'm going to be interested in plane trees, which are rooted combinatorial trees for which the edges are assigned a cyclic order. And somehow it turns out that there's a way of actually defining a continuum tree. And the way you define a continuum tree actually relies, first of all, on a combinatorial bijection. So a tree of this nature is actually in bijection with an excursion. And the way you go from the tree to the excursion is actually very straightforward. You just imagine, so a tree is basically a set of left-right calls, or ones and minus ones. And so you just sort of imagine exploring the tree. So here you're going up 1, 1, 1. So that's up, up, up. Come back down. So you come back down. So you sort of have an exploration process. And when you do this exploration process, you see that what you get is an excursion. So an excursion is a function that stays above. And you can go back. Okay, so somehow, if I give you an excursion, then you can actually reconstruct the tree. Okay, so this is a combinatorics fact. It's like one. So there's this famous problem in sort of Stanley's book on combinatorics on sort of the Catalan numbers, and this bijection somehow is there in that problem. So this is one problem with 66 parts. Okay, So it turns out that once you've seen that, you can actually sort of step out of the realm of, let's say, just sort of discrete objects and use excursions to define trees. Okay, so a real tree is a pointed compact metric space. And the way we're actually going to think about trees is just in terms of excursion. So I just give you a continuous function on, let's say, 0, 1, which goes up and comes back down. In fact, it just needs to be above. Then I will construct from this a tree by basically taking the interval 0, 1 and introducing on it a quotient relationship, which is obtained from the excursion. So the quotient relationship is that I say that 2 points are identical if somehow, wait, let's see, which 2 points on this figure do I want to be? Okay, I mean, maybe, did I give you the quotient? Okay, so the relationship is that 2 points are the same if, so you identify 2 points if the function lives above them and doesn't sort of go back below it. So I take, the continuous function. If I have an interval on which the function lies above, then I just say that these 2 points are identified. Okay, so there's a sort of simple recipe that takes an excursion, and from the excursion you take a quotient relationship.
So you're getting embedded.
No, what I get is a metric space. I get a metric space which is a subset of 0, 1,
Yes.
and the metric on this subset is given in this way. So the distance between 2 points is somehow you use the function, and then it's the minimum that lives in between them. Metric space, and for me a metric space is a particular subset of 0, 1. That's it.
And so how do okay? So by analogy, that's a tree, or
Yes, it's an extension of the definition, right? So so over here, yeah, that's exactly right. So here is the discrete tree. I found a set which is in bijection with it, and now with this set I know how to generalize, and I check that the generalization works on this particular discrete family of functions, and then I say, well, these are the properties that I need of a tree, and so therefore I can do it for arbitrary functions. Okay, yeah.
Now the discrete one has Lipschitz constant equal to 1.
Yes. Yeah.
So are you imposing any?
No, absolutely not. And in some sense, that's precisely the point. The point is actually, and the reason I mentioned these excursions, is that there's the reason I care so much about paths like this, so of course they correspond to sort of the set of plane trees. So one can enumerate the set of plane trees that's given, it's one of these enumerations which is given in terms of the Catalan numbers. And now one can imagine sort of taking a scaling limit of this object. So this looks like a random walk which is conditioned to be positive, and in fact it is. And we know exactly what the scaling is for the random walk, so you want to rescale these guys by square root of n, this guy by 1 over n,
So
and you get a limit.
The Lipschitz constant.
Absolutely not. So what you get, the kind of fundamental object that we're actually interested in, is that there is this canonical continuum tree. So there's a canonical scaling limit of trees, and this canonical scaling limit was basically found by Aldous, and it's called the continuum random tree. And the continuum random tree is basically the scaling limit of the excursions that I showed you. Okay. So by now there's this kind of huge literature that surrounds the CRT, and so we believe that the CRT is kind of this important object in mathematics. And so let me just summarize this part. I think it took a little bit more time, but it doesn't matter so much. Okay, so the first part I want to say is just that conformal maps with branching appear in math and physics. I mean, there are sort of models that are known, but there are basically no rigorous results, very few rigorous results in these models. This is not something I said anything about, but it's that there's another approach, but this approach doesn't lead very far. And so the main point really for us is that I was aware of the theory of the continuum random tree. And so it's kind of natural to guess that limits of DLA or Hastings, I mean, this is just based on some aesthetic principle. You've got one beautiful mathematical object, you've got one beautiful simulation, which has a sort of limiting tree. We hope that these guys should be related. But in some sense, there's just no way to get from the CRT to these limit shapes. And so what we wanted was to find a model where we could actually say something interesting. So let me show you simulations of our model. So first I'll show you the pictures because I want to turn off my computer and switch to the blackboard. So here's the kind of trees that we are creating, and I will tell you in a second how these guys are created. But first it's a nice picture, and I was very happy when we found this. Okay, so this is a particular growth process that we are introducing. In fact, I actually don't have any theorems that go with this one. I have theorems with the next image that I'm going to show you. And I'll tell you in just a second how these pictures are created. Okay, there are numbers up top which basically tell you what the object is. Okay, so let me show you the one for which we can actually say stuff. Okay, and this is a similar one, but you'll see that it's a little bit more regular than the previous one that I showed you. Okay, and on this one we can actually prove a whole bunch of theorems. Okay, so at this point let me stop with the model, and I'm done with my computer.
Are Galton Watson trees?
Oops, sorry.
Yeah.
Yeah, I'll define them in a second.
Yeah,
Yeah.
But they're not embeddable in 2 dimensions, are they, in general?
That's the theorem.
Huh?
I will give you a theorem that says exactly that. Okay. So first let me now tell you what our model is. Okay, so here's the model. Okay, so the combinatorics. So I'm not going to sort of start with the lattice model. What I'm actually going to do is to start with combinatorics. So the combinatorics is based on a binary critical Galton-Watson tree. Okay, so let me just say what that means. Okay, so I'm thinking about having a tree. Okay, so I have a mother. The mother has 2 children, or let's say an independent number of children. Okay, so the way the tree is constructed is that population so time is integer. Okay, and so yn, the rule where, so first of all, xjn are IID with probability xjn is equal to 0 is the probability that xjn is equal to 2, which is equal to 1/2. So you have sort of even probability of either having 0 children or 2. So it's called critical because somehow, on average, there's only 1 child, and it's known that if you have a situation of this nature, then in fact, the tree. Let me see if I wrote down anything more specific than that. Okay, I didn't. So it's kind of a. So I just start out with 1 person, so it turns out that this is basically the structure that you get. Okay, so the way we're going to do it is that we're just going to assume that this guy is given. Okay, so there's a combinatorial part that's given. And now what I will do is I will actually introduce a spatial part. Okay, so I'm going to use this guy to tell me how many people I have at any given time, but I'm actually going to introduce spatial motion. So this is going to be the driving measure. Okay, so I'm just going to focus. So, let me take, let's say, the kth interval of time. Okay, so so I'm going to solve the stochastic differential equation, which is dxj. Key not equal to j to xj x key plus 2 b w g. So this is it's going to be on the on the end. So what's going to happen is that I'm going to sort of solve this differential equation, but the initial condition for this guy, xj, so okay, how do I put this? Maybe I should not be. Let me sort of explain it just right next to this picture. Rather than give you the formula. So somehow at this point, I start out with some particle, and then I solve that. So actually over here, I start out with a doubled particle. So I'm always starting out with a singular initial condition, which causes two particles to split apart. So somehow there'll be two particles that will move apart. And then at the first time, this guy dies. This guy keeps going. It branches into two pieces. Then at this point, that guy dies. This one branches into two pieces and it keeps going. Okay. So over here, I've just, in general, if there's a little bit of noise, these guys are going to jiggle around. Okay, so somehow the coupling between, so in each level over here, you're basically starting out with two particles at a singular initial condition. Then these guys move apart, and then you solve this differential equation. Okay, so it's a theorem that this differential equation has a solution starting out with this singular initial condition. And it's a really very special property of this particular differential equation. And this differential equation is called Dyson-Brownian motion. Okay, so what we are doing is we are choosing as a driving measure for our Lovener process a Dyson-Brownian motion, which is a branching Dyson-Brownian motion, which is starting with the tree. Is the model clear? No.
This depends on being critical?
Yeah, so it depends upon being critical. So the critical part really is related to having the fact that I want to get a good scaling limit, and for the scaling limit, I need it to be critical. But just to define this differential equation, you do not need to do that. You could start out with any branching process. And so all that matters for me is that I want the branching process because I want control over the combinatorics. But aside from that, it doesn't matter so much. Okay.
So how do you? So I understand the Dyson-Brownian motion, but how do you hook that up to your combinatorics again?
So it's just that the Dyson-Brownian motion is holding on sort of each time interval between branching times.
Okay.
So it's a system of differential equations, and they're sort of coupled between different times just by the initial condition. So if I'm on this time slice, so let's say I was solving on this time slice.
Yes.
So I know whatever my position was at t just minus.
Okay.
And then at this point, what I do is I add a new particle. So I start out with a doubled point for Dyson-Brownian motion at this point. And it's a theorem that if I start out with a double point for Dyson-Brownian motion, it's immediately going to split apart.
Okay.
So there's a well-defined solution to this differential equation, starting with the condition where you've got 2 points over here. You let these go, so there's a theorem. It's just going to push apart nicely.
Yeah.
Then at the next branching time, you kill some of them, and at the birthplaces, you add a new guy.
When do you know when to? I don't quite know when you know
When I
start the next branch.
Oh, so I've chosen these times over here just to be integer times. I have a branching process in discrete time just because it's the simplest guy. Everything would work just fine in continuous time, but this is just the easiest. So it's just I'm solving this SDE on different bunches of times. Okay, so I solved this differential equation, and when I solve this differential equation, what I would do next is to define
What weight do you give each xj?
so each xj is going to be just, well, 1 or actually 2. So what I'm going to do is I'm going to define the mu t to be 2. Let me write it out as j. So let's say particles alive at time t. That's a better way of putting it. Okay, so that's it. That's the model. So that's the stuff, the pictures that I was showing you. There was one picture.
What's the significance of the number 2?
It just works nice. No, it should be just 1, but the formulas are actually cleaner if you put in a 2. So the 2 is sort of, it's to do with the SLE convention, where you have a 2 in there which measures the half-plane capacity. So that's basically the only reason for the 2. Okay, so I showed you 2 pictures. So there was the one where the stuff is really jiggling around. So that one has a sort of, a finite value of beta. And then there's the other one where, it was not so smooth, and that turns out to be infinite beta. Okay, so let me state a couple of theorems. And then I'll tell you why somehow we are where we are. Okay, so theorem 1. So this is all, this is really no spatial noise. Okay, so theorem is the following. So I want to get the precise statement. Okay, so for each okay, so let me just remind you that this measure mu is going into this differential equation, and I'm running the Loebner evolution, and I'm getting a family of these boundary type domains in the complex plane. And the game is really to understand the geometry of these guys, given sort of the input that you put in. Okay. No. Okay, so I started out with the tree. So the tree is just a combinatorial object. And I've taken this combinatorial object and I've sort of constructed a set in the upper half plane. And so what I mean, okay, so I've actually got a time parameter running this way. And so at any finite time, I can just restrict my tree to that part. Okay. So for any finite time, I will see, the image that I'm seeing in the upper half plane is going to be topologically exactly the same as that guy. But in fact, we can say a little bit more. So what I mean by, I didn't quite define what graph embedding means. So in particular, the edges of KT are analytic arcs. Okay. In the upper half plane that meet. And so this part actually made us quite. So this is in some sense why we put in the factor of 2. They meet at symmetric triple junctions. Okay, so this is of course a triple junction where each of the tangents is 120 degrees. So somehow, you want the angle, you want to get the angles right for conformal mapping. So you want to get the tree with the angles at the tree being exactly right. And so that's basically achieved by this particular choice of the Loebner evolution. So there's a kind of magic in Dyson Brownian motion, or just Coulombic repulsion. And somehow if you feed into the Loebner evolution Coulombic repulsion, it just has somehow exactly the right properties. Okay.
Would you say what you mean by the hull here?
So the hull is always the set that you're getting from. So Loebner evolution is just about conformal mapping. Yeah. So we have to have a simply connected domain which we are sending to the upper half plane. The hull is the complement of the simply connected domain that's being mapped over here.
Okay. You mean
it's the boundary. Yeah. So it's the boundary of the region that I'm mapping conformally over there. So it's I guess terminology from conformal mapping theory. So the game in Loebner theory is to construct the hull. So you choose SLE kappa. So you're choosing a particular driving measure, yes. And you want to get. You want to understand
the structure of the hull.
Yeah, you want to understand the structure of the hull. That's exactly it.
That kind of thing.
Exactly. Okay, so over here the key is somehow So I should have said this at the very start. So somehow. What happens when you're doing, this is sort of a classic fact going back to, 1920s and to Loebner. So the natural topology on domains that sort of conformal mappings use is always the topology given by the analytic function. So you've got a family of analytic functions which are converging, let's say, uniformly on compacts in the upper half plane. That means that somehow you're also going to get a convergence of the associated regions that are being mapped by the Riemann mapping theorem. But that convergence is very, very weak. So it's the sort of, this is called Karat-Theodory convergence. In particular, it does not actually imply that, so convergence of driving measures does not imply anything basic about, it doesn't imply any sort of nice properties of the hull. So the fact that, so you could choose, somehow you could choose a different driving function over there where you start with a branch point and push apart. But it turns out that you have to push apart at exactly the right rate so that you actually, so that the embedded tree has the same topology as what you started with. And somehow if you push with, so the factors of 2 over there are kind of cute, but they actually lead to exactly the right triple junctions down here.
Well, what do you mean by triple junction?
So what I mean is that, so here's the combinatorial. So, okay, so I've gone from, okay, maybe I should put my picture over here. So here I've got the combinatorics. So here I've got combinatorics plus spatial motion. So it's just spatial motion on the upper half in the real line of the points that are driving. And then I'm sending this guy, so now there's a conformal mapping. And so what's happening over here is that I'm growing a tree. And the point is that, okay, I'm not sure if my figures are that good, but each of these arcs is analytic. And at this point, I have a 120-degree angle at every single one of the vertices. That's what I mean. Okay, so that's kind of the, okay. So that's the first result. So as you can see, somehow, I've stated a kind of general driving function, but the theorem does not include that general driving function. And so we are still stuck on it, and it comes down to somehow a way in which this theorem is proven, where sort of we really need a sort of fine blow-up analysis. And this is, in SLE, this is kind of known to be difficult. As soon as you put in the sort of stochastic perturbation, things have to go wrong, and we don't quite know sort of how to control that just yet. But this would in some sense this is a kind of fundamental object in random matrix theory, which is why we chose it, and we believe it will work more generally. But at least this is what we can prove right now.
This is true for finite beta.
This is, well, I don't know. I get nice pictures, but that doesn't say very much. The nicest picture we have is for some finite beta, but I don't actually have a theorem.
You don't see any transitions as you vary beta or anything like that?
We are definitely not at that fine level yet. So in fact, even getting this sort of completely right is still sort of stuff that we're doing.
I was just read the comment that if beta is too small,
Yeah.
you have collisions.
Oh yeah, absolutely. So yeah. So of course, so we know, yeah. So that's right. That's completely right. So with SLE itself, you know that so the kappa is working like an inverse beta over here, and so once it gets too small, so I'm not sure if it's at 4 or something like that, but there's definitely something is going to go wrong, but I don't know to what extent. Yeah. So, okay. So the one of the reasons we sort of worked with this guy is that somehow I've got this point process on the line, and the reason we started with these branching processes is that we know how to take scaling limits over here. So I'm going to write out the scaling limit and then tell you what we can prove about the scaling limit. So the scaling limit. Okay, so I'm going to write down an SPD. I'm going to write it down assuming, so it's just cleaner to write it out for the density. But of course, we don't use a density anywhere, so let's assume ut has a density. Density rho. Okay. So let's say rho of xt. So our assertion is that this driving measure has a characterization in the limit going so there's a sigma, so there's a parameter over here. So over here, it's minus infinity less than x less than infinity, t greater than 0, and over here, rho x. So there's some initial data, which is going to be determined in a way that I will tell you. And so over here, H is the Hilbert transform. So H rho of X is the principal value over, what is it? Let's say 1 over pi. Okay, so it's so within this PDE, you can think about this as a velocity term, and the velocity term is determined by the Hilbert transform. And so this is a fixed parameter that basically will depend upon the variance of the approximating particle process. So it need not be that one. So it's a fixed parameter. And W dot is space-time white noise. Okay, so there are basically two theorems. So one theorem that go with this kind of limiting equation. So one theorem is the fact that this limiting equation is well posed. So that means that somehow it's a stochastic PDE, but if I choose a finite some initial measure, then the stochastic PDE is well posed. So okay, I mean that's not stated in terms of the densities. It's a sort of theorem about an associated martingale problem. But the main point is really just that there is this kind of limiting object. So there's a limiting object, and it's a limiting object. So there's a second theorem that basically says that if you scale these guys in the right way, then the subsequential limits will sort of limit to this PDE. Okay, so perhaps I should state the two theorems. Actually, maybe I should take a breather because I don't want to write too much, and it's 4:30 or 5 on a Friday evening. So is it clear to you guys what I'm trying to do? And then I can tell you somehow.
So is this related to equations and some toy equations and fluids that people use?
I'm not sure if it's related to toy equations in physics, but it's related to, I haven't seen it come up. I haven't seen this equation before. Well, okay, I've seen it before in the sense that we came up with it.
I know,
but I haven't, yeah, okay, so there are blow-up problems in fluids, so toy blow-up problems.
Yeah.
That's right. Without the noise, and you try to, it depends very much on the sign of rho. So if rho is positive, actually it's completely trivial to solve analytically. It's completely trivial because you take the Cauchy transform of this and you get Berger's equation, but in the complex plane. Okay, it's kind of important in random matrix theory, actually. So that's where it comes from. And so let me just make one remark. So this, or a couple of remarks. So remark one is that the SPDE dt rho, let me write it out in the following way. So I put a Laplacian of rho plus sigma squared rho w dot. So this could actually work for x in Rd. So this SPDE goes back to the 1960s. So this is called Dawson Watanabe. Oops. So the terminology superprocess is terminology of Dinkin. So process is just sort of probabilist terminology for a random function. So what's happening in these problems is that you have a measure which is randomly evolving, and so it's not just a function which is evolving, it's a measure which is evolving. So Dinkin called this a superprocess. And this model was introduced by Dawson and Watanabe. So what this model corresponds to, in a certain sense, is very similar to this, but it's a lot easier. So you again start with the same combinatorics, but the spatial motion, you just make independent Brownian motions. So I've got a bunch of Brownian motions, and they keep, they can be born and they can be die, but they keep moving around at random. And it's known that the scaling limits of this combinatorics spatial Brownian motion over here is given by this SPD. Okay, so it's not quite this SPD, it's actually for the measure that goes with this. So there are theorems that say that the sort of Markov process for the measure is well defined and has various sort of fine properties. So this is a sort of reasonably well understood process. And so you see that all that's changed from this PD to that one is that I've replaced the Laplacian with this term, which is rho times the Hilbert transform of rho. Now it turns out that this guy is kind of so this describes sort of the world of regular probability theory. It turns out that this guy describes the world, shows up in the world of free probability. So this one is the free probability analog of this SPDE, and we were really not looking for anything like that, but that actually showed up as a limit of our problem. So let me state the theorems that go with this. So in a sense, we believe that this is a very interesting sort of limiting object, and at least we have sort of partial results that say that it's an interesting limiting object. So let me just explain where the SPD is coming from. And then tell you why why it's the sort of right object.
But you're not claiming that it's the limiting object of what you...
Oh, so I am claiming it's the limiting object of this particle process. So you see that over here there's no, so in principle I can take this guy and I can drive a Lovener evolution. And so I know that, just on sort of soft grounds, I can prove a theorem that says that my particle system will converge to this guy, and therefore the hulls will converge. The problem is regularity. I don't know that the hull that I'm getting in the end is actually a tree in the sense of Aldous. That's what we're after, but we don't have the regularity estimates that actually tell us that. So we don't know that the density exists, and we don't know what the regularity is of the hull. So that's kind of the tough question, but we kind of know what we should be looking at. And as far as I know, this is the only sort of such object which actually exists, which even could be a candidate limit. Okay, so theorem 2 is basically, let me write it out. I don't think it would help me to actually, okay, let me state it precisely. Let me say with compact support. Then precise theorem is something like this, then the martingale problem. Let me give this equation a name. Okay, so informally, this is kind of the right framework in which you want to look for sort of well-posedness of the SPDE. So what it really tells you is that there's a well-defined measure-valued Markov process. Okay. So in some sense, the tough part of this theorem is really to get the uniqueness, or just on soft grounds you get existence always if you can prove tightness. But uniqueness is actually something which is a little bit delicate. And the reason it's delicate is that it's really to do with the singular interaction of the particles over here. But it turns out that there's kind of an exact solvability sort of sitting in the background, and that's what gives you the associated uniqueness over here. But I don't want to prove this theorem. What I really want to do is to just explain to you why you're actually getting this PDE, which is in some sense the most interesting part of it. The rest of it is actually just putting the pieces together.
You'd like some more regularity of this?
Yeah, so for example, so that's actually the most important remark. So
Yeah.
and that's very, so I would really like to know. So I sort of want it to be singular, but I don't quite know how singular I want it to be. I just don't know. Okay, so I believe it's very interesting. And it involves two effects. So somehow let me just give it to you an analogy with this one. So so this one we know more about. So this one we know that in dimensions greater than or equal to 3, or dimensions greater than or equal to 2 is special, but I know certainly for dimensions greater than or equal to 3, it has no density. In dimension in dimension d is equal to 1, it does have a density. So this is one of the sort of first sort of solid results on this one.
say it as a density, you mean it's absolutely continuous with respect to
I
the
say one absolutely continuous with respect to
But
the
then
bag.
irrespective of what is the initial data, or you...
So no, of course, you have to put in some assumptions into the initial data. And I don't know. I just have no. I don't know. So there's somehow, yeah. So there's the Hilbert transform piece actually gives you a regularizing effect, but I don't know how to balance that with the roughening effect of the other guy. And so somehow the regularity of this one is quite important, because the regularity of this one feeds into the Loevner evolution and therefore the geometry of the hull. And so I need to know what the hull looks like. I would like to say that my hull is actually some sort of interesting fractal tree, but I don't know how to say it because I don't know. This is the kind of, it's kind of tough thing that we were not able to. I don't know how tough it is. It's just like we didn't do it. We haven't done it. Okay, so the other theorem 3 is really that this is the scaling limit. So, and somehow since we're towards the end, so so this is sort of informally for the okay, so I want to explain this because this is actually, it's not at all hard. In some sense, it's really very, very soft. And once you've played with these objects enough, you understand where these terms are coming from. So there are two terms in this SPD, and I want to explain to you where both of them are coming from. So let me first explain where this term comes from. And because this is completely classical, and it goes back to Feller, and it's really in some sense just coming out of pure combinatorics over here. So I've chosen a Galton-Watson tree, and I've chosen a Galton-Watson tree to be critical. And now what I do is I consider, let's say, so I consider a bunch of Galton-Watson trees. Okay, and I let let's say xn, or let's say xt. So I just look at the total population size. Okay, so there's a sort of theorem that goes with these guys where you sort of assume that you've got enough of these particles. So we know that on average they're going to all die out. But you take enough of these, so you take sort of on order of n initial particles, and then you speed up time also by a factor of n. So, so the theorem is basically the following. So assume we take a sequence, take a sequence of these guys, and let's say at initial time, these guys are n times x. So you've got order n particles to begin with. So you start out with, let's say, n of these seeds. Let's assume x0. Okay, so you assume that the initial populations converge. And then, okay, let me get this right. Let me write it out this way. Let me make this a yt. Let me make it an xt to be equal to 1 over n and a y nt. Okay, so you're speeding up time, integer value. Okay, so the state theorem is just basically the following. Assume that the rescaled, so take a sequence of these guys, and assume that the initial data converges, then let me put it this way. Okay, so these guys converge in law to xt, where xt solves Okay, so this SDE is the SDE that describes the Feller diffusion, and this is one of the first scaling limits that was established for branching processes. And this square root is basically this square root over there. It's the term that you get only from the branching. So the noise in this problem has nothing to do with the fact that you also have the Dyson branching motion piece in there. It's really just to do with the branching motion. Okay, so the branching process in the end has a scaling limit, and the scaling limit in the branching process gives you a fluctuation. Okay, now where this guy comes from is really just a very, very specific property of the Dyson, the sort of Coulombic repulsion of particles. So it's really a miracle of the Coulombic repulsion that in the end, when you have Coulombic repulsion, you get the Hilbert transform. And actually, I can do it in a kind of clean way because it's a good identity to end the week at, and I'll stop there. So let me explain the appearance of okay, so the appearance of the Hilbert transform piece okay, so suppose I just take the following ODE. And rather than work directly with the particles, let me work with sort of the Herglotz function that goes with this. So let me look at P of ZT to be the sum of 1 over Z minus xj. Okay, so if x dot is evolving according to an ODE, this guy is evolving according to some equation. So you want to compute that equation. It turns out that, let's call this star, and let me write down so it's a cute calculation that you can check that this is equivalent to that one. So it's a miracle. So in the end, it's not a miracle. It's really just the cancellation which lives underneath the Hilbert transform. And by choosing this particular force, somehow you end up in a situation where you get this term. This is a term at the level of the Herglotz function. And if you were to sort of write it out at the level of the measure, this is what you would get. So this is where it comes from. And in some sense, this kind of sort of simple calculation actually lies at the heart of everything that we're doing. So I think yesterday Camilo told me, it's the analysis seminar, you have to give us a tough estimate. I was like, well, I don't have any tough estimates. So the whole point in this problem was just to find the right model. Once you find the right model, it just all follows. So we do have a tough estimate that we would like, but we don't have it yet. And if anyone is interested in it, I'm here for the whole year or the rest of the year, and I'm very happy to talk about it. But the result is really this, that there's a very clean model that one can introduce, which just sort of relates to Dyson branching motion. There's a reason for that, which sort of comes from other directions, but I think this is enough for, this is enough for this talk. So there's one last thing I want to say. So this corresponds to the Feller diffusion, but I started with this, the continuum random tree as being the central object. So the continuum random tree requires a conditioning trick, and it gives a scaling limit, which we can also write down, but that's a different SPD. This is the easier one to describe. That's why I started with this one, but there's an equivalent SPD for the. So we think these are kind of interesting limiting SPDs that we want to understand better. So, okay, that's the story. Thank you.